Okay, so in this movie clip, let's begin with the question: how to quantitatively evaluate the device performance of BJT? For example, PNP BJT. How to evaluate its performance? Okay, so for that purpose, we are going to learn the emitter efficiency stuff. But before moving forward, I guess. Since in the very last movie clip, I have stopped my lecture in this lecture note, so I'm going to begin with some brief concept of BJT electrostatics. It looks and it sounds complicated, but if you're well geared up with some fundamentals and basics of PN theory, PN junction theory, then this BJT electrostatics is a kind of extended version of PN junction diode. So let's take a close look at what the PGT electrostatics are. So as shown in this lecture note, you can see the cross-sectional view of a PNP BJT. So emitter base collector of PNP BJT. So as described here, under normal operating conditions, that means the emitter base junction, this emitter junction is forward biased and this collector junction is reverse biased. Then the BJT is working in active mode, as we have learned in the very last lecture note. This, right? So active mode. And then please think about how the depletion layers are formed within the PNP BJT. So as a hint, and as this stated here, the BJT, PNP BJT device may be understood and may be viewed electrostatically as two independent PN junctions. So I mean this PN junction plus another PN junction. And since this N side is commonly shared, so that you're going to end up with this PNP BJT device. So if you split this BJT device into two different segments, such as PN and another NP junction, then you can more easily analyze the electrostatics of BJT. So again, under normal operating conditions of this BJT, this emitter junction is forward biased, and this collector junction, I mean the base collector junction, is reverse biased. So as you have already learned, the depletion layer can be formed in between this emitter and base regimes. But herein notice that the P side, P-type doped emitter is more heavily doped, so that most of the depletion layer can be formed in the lightly doped side, in this case N-type base regime. Okay, so that's the reason why this shaded area is drawn mostly in the N-side regime. Okay, so this depletion layer width is denoted as a W sub EB, emitter base depletion layer width. And let's take a look at the collector junction side. So herein you can see the shaded area, and now this N side and P side is a more relatively evenly balanced in terms of doping concentration, so that the depletion layer in across base collector PN junction, part of the depletion layer has been formed in the P side, the collector side, and the other part of the depletion layer can be formed in the base side. Okay, but I guess herein from the perspective, from the drawn or illustrated depletion layer herein, we can simply guess that the doping concentration in the N side is slightly higher than the doping concentration in the P side, because most of the depletion layer has been already formed in the P side, which is lightly doped side. Okay, all right, so one more thing is here, the depletion layer width between collector and base is denoted as W sub CB, and here W indicates, the quasi-neutral region of base. Okay. However, the physical uh, width of base is denoted as W sub B. Okay, so W sub B and W is quite different. Okay, that is not the same to each other. All right, now along the x direction, let's draw the energy band diagram. Under normal operating conditions, that means emitter base junction is forward biased, base collector junction is reverse biased. Then can you draw the energy band diagram along the x direction? That's very simple. Again, this PN-PBJT is divided into two different parts. PN, emitter base, and another one is base collector. So you simply draw the energy band diagram for each PN side and then simply combine them together. That's it. So herein, emitter side and base side. Just forget this part, okay? Take a look at here, this part only. And this is a P plus, that base is N, and that is heavily doped, so that, the conventional PN junction diode, if I draw the energy band diagram along an X direction, this is a P side, this is the N side, and the Fermi energy level, the Venn diagram at thermal equilibrium. Okay, so E sub F is single valued, and intrinsic Fermi energy level can be drawn as dotted line, and the depletion layer has been well formed on both sides, so that in the P side you can see the band bending from upside up to downside, and the energy band diagrams band bending can be found on the inside depletion layer from upside to downward. Okay, up to downward direction. Okay, so this parabolic curvature can be well drawn when the p side and n side doping concentration is comparable to each other. However, if we go back to this emitter base junction, this emitter side is more heavily doped. So this part, right, can be cannot be drawn explicitly because the depletion width obtained from or coming from the P plus side is very, very narrow. It's hard to see the parabolic curve here. Okay, it's hard to see. So only this part, okay, this part only drawn. Okay, okay, so if I draw it again, only like that. Okay, so you don't need to draw like this, up, upside down, downside up, like that. That's not true, because this depletion width is much, much smaller, narrower than the depletion layer coming from the inside. So simply straight line and the downward. Okay, like that. Okay, all right, let me draw my notes just to clearly show you the energy band diagram between P plus and N, or emitter base junction. Okay, all right, and now is the turn to draw the energy band diagram for a base collector junction. Okay, so this is another PN junction. So as we have learned, the P side, EF, EV, you see, and this is the N side. So EF is single valued one, and this is N side. So oops, conduction band is very close to the Fermi energy level, and valence band is here. So maybe the band bending can be found drawn like that. Okay, so you can clearly see that. See my energy band diagram again here. So this is base part conduction band edge, and band bending here and there. But notice that most of the depletion layer has been formed in the lightly doped side one, which is a collector. So most of band bending can be actually happened on the collector side. Take a look at here. Most of the band bending has been happened in the collector side, and up to downward band bending is relatively smaller. Okay, so you can Very finely, you can draw your own energy band diagram along the x direction for BJT, PNP BJT device under thermal equilibrium, because this Fermi energy level is single valued one. And again, since the BJT is operating in active mode, so this PN junction diode should be forward biased, and that PN junction should be reverse biased if your BJT is working in active mode. So usually the active mode is a preferred one for the application of signal amplifier. Okay. All right. So in the upcoming this lecture note, take a look at the electrostatic potential along x direction, as well as electric field along x direction, charge density along x direction together. So at a time, I have drawn all three different plots to show the electrostatics for BJT, which is a PMP in this case. So as we have already learned, charge density plot of P plus N junction, most of the this is a donor, right? Donor is positively ionized, and this is a acceptor, right? Negatively charged one. So this HY, which is minus Q times N sub A, and this value should be Q times N sub D. And if I estimate the area of both sides, the area should be identical. So minus Q times Na times, and this depletion layer width is usually minus XP, is identical to the Q times N sub D, and this depletion layer width is denoted as X sub N, and they should be identical. Okay, so we have already done this work, right, using a charge neutrality equation. And from the information and from the curve of charge density versus X, we can simply draw and induce the electric field versus X direction, E versus X. What was that? How to get it? Yes, Poisson's equation. So dE dx is proportional to the charge density, and this proportionality coefficient is equal to the, or defined as dielectric constant. So dE dx is identical to the charge density divided by epsilon silicon, because we are using a silicon material. Okay, so using this first order differentiation, you can simply draw the E versus X plot as shown in here. And definitely this slope is very proportional to the doping concentration. So if your doping concentration is very heavy, then you can see very steep slope. But if your doping concentration is relatively lighter, then slope is less slopey. Okay. And what about the potential? From the E versus X plot, your potential can be simply obtained using this mathematical equation. So by taking the integration work with respect to x, then you're going to simply estimate the potential as a function of x. So, but since the potential value is, should be defined one single, no, a certain way. Usually the quasi-neutral region of emitter is defined as a reference voltage, so 0 volt is defined here, so that this potential difference can be defined once your reference voltage is used and defined in the emitter side. And then using this first order differentiation, you can simply estimate all the equations for this. So actually we have already done this quantitative analysis when we have learned the one-sided PN junction diode. Okay, so if you unfortunately forgotten all the details for the quantitative analysis of one-sided P plus N junction diode, please go back to the movie clip that I have recorded, or refer to the lecture notes for that, or go to the textbook, PRS book, and read out all the sentences and all the corresponding chapters. Please refresh your memory. Then come back to this part. Then you may feel much comfortable with your recently refreshed memories. All right. Now let's move on to the right hand side, this part, base collector junction. So everything is almost identical when uh, what we have done for emitter base junction. So herein base collector junction, this part is again plus Q times N sub D of base. So instead of ND, I'm going to use the N sub B, base doping concentration. But since we are talking about the PNP BJT, definitely N sub B indicates the donor's concentration in the N site. And this part is corresponding to minus Q times N sub A, but instead of this emitter, minus Q times N sub E, because this is the emitter stopping concentration. Since we're talking about PMP, so definitely this N sub E is N sub A in the emitter. Okay. So with the same, algorithm or steps, you can derive E versus X plot and V versus X plot from the EX plot. So please do that, and everything is same as we have learned in p-n junction theory. Please have your own time and try to draw these three different plots by hands. Okay. All right. Now uh, let's go back to the question that I have raised up in the very first second of this movie clip. How to measure, how to evaluate the device performance of BJT. Well, for the given voltage difference, if this BJT device can flow much higher current, then that should be okay. But that sounds very simple. Any other way, any other more fine-tuned method to quantitatively, not qualitatively, quantitatively evaluate how good or how bad the BJT device is. Okay, so go back to the cross-sectional view with how the carriers are moving under under bias. Okay, so again, this under normal operating biasing, say forward biased emitter base junction and reverse biased base collector junction. Then, since this is a P plus side, so many holes would be injected into the N side, which is quite identical to the forward bias to PN junction, right? So once hole has been well injected into the N side, they're gonna become the minority carriers in the N side, and they gonna diffuse toward the collector side, but part of it, so as drawn in here and denoted as number 1, part of the injected holes from emitter should be recombined with the electrons, which is the majority carriers in N side or base. Okay, and then rest of them can be well arrived in the collector side. So how efficient the holes are delivered from emitter to collector. So to measure this, delivery performance, device engineer has come up with this metric named as emitter efficiency. Okay, so emitter efficiency indicates the total amount of holes injected into base and how much holes are well survived and arrived at the collector side. Okay, so this is denoted as the I sub emitter uh, induced by holes, and part of it will be lost, and in the end the part of the holes would be survived and well arrived in the collector side. And one more thing is this: since this is a P plus N junction and the junction is forward biased, so that electrons can also inject it into the p side. So if you think about the current direction, electron is now moving from right to left hand side, so that the current is flowing from emitter to base. So this is another current component when you are talking about the IE, I mean this current. And if I'm using a circuit symbol, emitter, base, collector. So when we are draw the I sub E, this I sub E is most likely comes from this holes movement. However, don't forget this electron movement. Okay, so total amount of emitter current, IE, consists of two current components, I sub EP, this, and I sub EM, this. Okay, all right. Then, emitter efficiency has been well used to quantitatively evaluate the BJT performance. So, the way to enhance the emitter efficiency is this. My question is how to increase the emitter efficiency. But if you take a look at the component here and there, well, the maximum value should be 1 because I sub En cannot become 0 because this is an n-side, so very tiny amount of electrons would be injected into the p side, emitter side, once this emitter base junction is forward biased. So ideally, we would like to suppress the total amount of electron injection, the I sub En, uh, down to 0, but that's ideal, but almost to 0, right? Therefore, IEP divided by IEP plus something. So this value, the maximum value of this metric, named as emitter efficiency, should be 1 or less. Okay. Then what is the engineering solution, or how to design the BJT device to obtain or to achieve emitter efficiency of 1? How to get the maximum value of emitter efficiency? The answer is very simple. I sub p is much higher than I sub n. How to do that? Well, if emitter side is very heavily doped and base side is very lightly doped, then most of the holes are injected from p to n. But even though the small tiny amount of electron has been injected into the p side, but this amount of injected electron is almost negligible compared against the total amount of holes injected into n side, because this p side is much heavily doped. Okay, so to achieve the maximum value of emitter efficiency, how to design the BJT? Yes, emitter doping concentration should be much higher than the base doping concentration. That is very simple solution, and that is a basic device design guideline for BJT. Okay, and next one, let me erase my note and take a look at the right hand side. Here, base transport factor. What is it? So that uh, is well known performance parameter for BJT, base transport factor. So think about it's the physical meaning of it. Base transport factor. Okay, base transport. Transport means, something is moving from A to B. Okay, and base, indicates the name of the regime of PNP BJT. So in this case, n-type base. How much something is transported, something has been moved, delivered, and that is counted as a factor. So here in alpha sub t, t from t in the word of transport, and if you take a look at the definition of it, is I sub Cp divided by I sub Ep. So I sub Ep is the emitter current induced by hole, and I sub Cp indicates, collector current induced by hole. And take a look at this white colored line, white colored arrow. And this part is denoted I sub CP. Oh, no. I sub EP, emitter current by hole. And while these holes are diffusing from emitter to collector, part of the holes are recombined with electrons in this base material, so that say 100 holes are well injected into the base and the 90 holes are well arrived in the collector side. In other words, 10 out of 100 has been lost, has been recombined with electrons. And then 100, 90. Okay, so this 90 indicates the I sub CP, and this 100 indicates I sub EP. Then base transfer factor means how much injected holes has been lost or has been recombined with electrons in the base. Okay, so you can simply come up, you can simply uh, estimate the maximum value of the base transport factor. What is it? Yes, 1, right? This ICP would become approximately very identical to the I sub EP if this recombination is very minimized. Then your base transport factor would become, in the end, 1. Okay? Then the question is how to achieve the maximum value of base transport factor. How to get the value of base transport factor, I mean the alpha sub t. Where's my pen? Yeah, here. Alpha sub t. You would like to make alpha sub t 1. What is the device design guideline for this? How to do that? You would like to minimize the recombination events in the base. How to do that? Maybe you would think, well, we can make the base very lightly, super lightly doped. Then the total number of electrons available in the base would be minimized so that the injected holes from emitter to base would be well delivered to the collector. That sounds reasonable, but is it the ideal solution? Is it a reasonable solution to have alpha sub t of to be 1? No. Always part of the hole, injected holes would be recombined with electrons in the base. Then what is the engineering solution then? Let's take advantage of using the diffusion length, the concept of diffusion length herein. Please ask yourself the definition of diffusion length. What is it? Yeah, the physical meaning of diffusion length is this. Average distance of minority carriers can survive before being annihilated with the majority carriers. If you think this sounds very complicated, please go back to the my lecture note talking about diffusion length, maybe chapter 3.2, diffusion. Okay, please review it and come back to this lecture note again. So going back with that in mind, I mean with the concept of and physical definition of diffusion length in mind, then what is the engineering solution to make alpha sub t to be 1? First, let me draw the depletion layer first. Okay, and this quasi-neutral region of base is denoted as W, and the physical width of the base is denoted as W sub B. So if this quasi-neutral regime, the total width of base is much shorter than the diffusion length of hole, this, then what would be happened? As we have already learned, think about the narrow base PN junction diode, hypersine, hypercosine stuff. Did you remember it? Yeah. So if W, the quasi-neutral, the width of the quasi-neutral base regime is much shorter than the single diffusion length, then most of the holes would be survived without, on average, without being recombined with electrons in the base regime. Most of the electrons injected from emitter can be well arrived into the collector regime. Okay, so please think about how short, how narrow the base regime is in the BJT. I mean, to have your BJT device to work appropriately. All right, now let's take a look at the last line in this movie clip. Common base DC current gain. So common base, we have already reviewed the three different configurations in BJT: common emitter, common base, and the common collector. So herein I have used the common base. So base electrode has been used as a common node for what? Yes, for input signal and output signal. So in this case, in the case of PNP BJT, the input signal, input voltage would become the voltage difference between emitter and base. What about the output voltage? Yes, the voltage difference between collector and base. Okay, so here in the common base configuration, the DC current gain, denoted as alpha sub DC, let me write down here, alpha sub DC is defined as input signal, in this case I sub E, and the output signal, in this case I sub C. Just a few seconds ago, I have used the word the voltage difference between emitter and base as an input signal, and the voltage difference between base and collector. But since a BJT device can obtain the current as an input or output signal, so herein I have used the I sub E as an input signal, I sub C has been used as the output signal. But herein, definitely base is a common electrode. All right, so IC divided by IE. But if your emitter is very heavily doped, and then I sub E, I mean that this I sub E is IEP plus IEN. But since the P side is very heavily doped, you can ignore this part. Okay. And what about here? I sub C, collector current. So collector current is this, right? And most of it coming from the injected holes, I sub CP. Okay. So alpha DC, common base DC current gain, the input current versus output current, is defined as IE, IC. However, this IC is most likely come from the whole collector current, ICP. Okay, then I guess from this you can get this relation. How to do that? So again, alpha DC. No, let me write down here. Alpha DC is defined as IE, ICP. Let me make IEP. Yes, just I have used the IEP here and there. This is IEP. So IEP divided by IE is here. Can you see that? This total is IE, right? So IEP divided by E is identical to the alpha. So the first term is gamma, immediate efficiency. And take a look at the second term here, ICP divided by IEP. Yes, this, right? So times alpha sub t, base transport factor, emitter efficiency. If you take a multiplication of both terms, you're going to end up with alpha DC, which is a common base DC current gain. Okay? So if you this sounds complicated, take your own time and summarize what we have learned from this movie clip and from this lecture note, and be familiarize yourself with the three concepts: emitter efficiency, base transport factor, common base DC current gain. Okay, and those three factors are well connected to each other. Okay. All right, I guess before wrapping up my movie clip, uh, just a single lecture note has been left. So let me explain it before closing this movie clip. Take a look at the title of this lecture note, Collector Current of PNP BJT Device. So collector current means here, how much current is flowing out of the collector side. Okay, so this emitter current, base current. So if I sum them up, I mean the IB plus IE is equal to IC. Then collector current. Let's see. No, I guess I was screwed up with the direction again. IB should be yes. Yeah, yeah, yeah. This is a IEEE convention. So in this BRS book, the IB is base current is flowing out of the base regime, not into the base regime. Okay, so instead of this IE, that is kind of input current, right? The IE, this is equal to IB, this part, plus IC. If I draw the circuit symbol, so this is IE, that is IP, that is IC. So in this BJT device, the input current is IE, and two output components can be found and drawn here, IB and IC. So IE should be equal to IB plus IC. Okay, so with that in mind, let's think about the collector current in more detail. Collector current is comprised of what? Yeah, I guess there are two dots, so bullets. So I guess you can guess two components for building up the collector current. That's right. So the number one is, as described here, take a look at the two. Yeah, this. The holes injected from emitter. I mean, this hole, right? Now injected from emitter, right? Which do not recombine in the base. So just forget this part, the recombination stuff. And uh, the holes are delivered and transported into the collector side. So this part, okay, number two. So this number two would be part of the collector current I sub C. But is that the number two is all of the collector current? No. Take a look at this. Since base emitter is now reverse biased, so part of the minority carriers near or at the edge of the depletion layer can be diffused into the depletion layer. Once they are injected into the depletion layer, they're going to be drifted into the other side because of the built-in electric field in between, maybe from this side. So reverse saturation current of collector junction, I mean this PN junction, right? This PN junction, once this PN junction is well reverse biased, then saturation current, a very tiny amount of current is flowing. So that is denoted as number 3 and illustrated herein. So number 2 and number 3 is the two components for the collector current. Okay, so now let's write down the equation for the collector current. So IC, we would like to write down IC as a with a two current component. So here number 3 is denoted as here. So in PN junction diode, the saturation current is denoted as I sub naught. But since this saturation current is flowing in between collector and base, so CB has been included additionally. And take a look at here. That is IE and that is IC. How they are transported. Yes, just a few minutes ago, we have learned that alpha sub DC, common base current gain. So base is a common, okay? Then how much electron input current has been well delivered to the opposite. So the current gain, alpha sub DC, can be used to how much emitter current has been delivered to the collector side. Okay, we're almost done. So from this equation, so as I have told you, input current is IE and the output current is IB and IC for this single BJT device. So instead of IE, plug in IB plus IC. So you can see that here. And from this equation, let's do one more thing. This IC, right? And IC. So let me write down here. IC is equal to alpha DC IC plus alpha DC IB plus ICB naught. So let me move this term onto the left hand side. Then 1 minus alpha DC IC is equal to alpha DC IB plus ICB naught. Okay, and take this coefficient into the right hand side. Okay, then here 1 minus alpha DC, oops, DC, and here 1 minus alpha DC. Then you're gonna get this equation. We're almost done. And this alpha DC over 1 minus alpha DC is defined as beta, and the ICB naught divided by 1 minus alpha DC is defined as I sub CE naught. So CE means a collector emitter, right? So collector emitter saturation current. So once PN diode is reverse biased, the saturation current has been flown. But this saturation current would be flown from emitter to collector side. So that is interpreted as ICE naught. What about this beta? Beta has been well described here. Common emitter DC current gain is defined as beta. So gain, when we have done for defining the common base DC current gain, go back to that common base here. Common base DC current gain, alpha DC. Beta DC indicates a common emitter in this case. So that emitter is common, right? So that beta is input, collector is output. So input current, base current, output current is collector current. Okay, so beta DC definition of it is very simple. IC over IB. And now go back to the equation here. Let me write down here. IC is beta IB plus ICE naught. But since this second term is very small value compared against this beta times IB, so this value is negligible. So you can just remove it. And then take a look at here. Aha, beta is IB, IC. Okay, good look at here. All right, we're almost done. Then this beta just remove a second term. Then this beta should be identical to this part. Okay, so beta is equal to what? Alpha dc divided by 1 minus alpha dc. But the question here is, what is the maximum value of alpha dc? Alpha dc was gamma times alpha t, and that is, gamma times alpha, that is gamma times alpha t. And the maximum value of gamma is 1, and the maximum value of alpha t is 1. 1 times 1 is 1. So 1 divided by 1 minus 1, 0. 1 over 0 means almost infinity. So beta is very high. So if your undergraduate major is electronics, then you're familiar with BJT is intrinsically uh, BJT has a higher gain than the MOSFET-based amplifier. Why is that? This gamma alpha T is almost 1, if say 0.95 and gamma is 0.95, plug in the value here and calculate the value of beta. Then you're gonna end up with a few 100,000 values. So this is the core part. Why the beta, the common emitter DC current gain of BJT can achieve 100,000 gain. Why is that? The base current is super small, but collector current is super high. To achieve it, gamma emitter efficiency, alpha sub t base transfer factor, they should be well maximized. For that purpose, how to design the BJT device? Yeah, simple number one guideline is emitter side should be very heavily doped. And number two is what? Yes, the diffusion length of holes in the base region, LP, should be much, much longer than the quasi-neutral region of base width. So always think about this. Emitter doping concentration should be very high, and the diffusion length is much, much longer than the base region. In other words, the base of the BJT device should be very, very narrow, even narrower than the diffusion length of minority carrier. Then you should be okay, and your device, your BJT device, should work very well. Okay, so please review what I have learned and take a look at the summary slides by yourself, and see you in the next movie clip. Bye bye. Thanks.